Hi everyone. In the previous lecture, I was talking about the existence condition of the Laplace transformation. Now in this lecture, I will now give some formulae of Laplace transformation, then some properties of the Laplace transformation. So first of all, I will give the formula for the Laplace of ft, where your ft is e to the power n. So Laplace of ft, using the definition, we have 0 to infinity e to the power minus st ft dt. So this is equal to e to the power minus st t to the power n dt. Now we have two choices. Either we can integrate by part up to n times so that this t to the power n remove, and another option is that you can use the definition of the gamma function, which is equal to, we can also write it this one. Then using the definition of the gamma function, this will become gamma n plus 1 upon s to the power n plus 1, because we have the definition gamma n upon s to the power n is equal to 0 to infinity e to the power minus some k x, or as we are using s, so this will be your this integral. So integral 0 to infinity e to the power minus sx x power n minus 1 dx is equal to gamma n upon s to the power n, where s is the multiplier associated with x and n is the power of x. Now if your n is positive integer, then it is equal to factorial n upon s to the power n plus 1. Now for example, if our n is 0, then Laplace of t to the power 0, that means 1, is equal to, if we put n equal to 0 here, then we will have factorial 0, and this is equal to 1 upon s. Similarly, Laplace of t, that means when n is 1, then this will be your 1 upon s square. So you can say that the Laplace inverse of 1 by s is equal to 1. From here, the Laplace inverse of 1 upon s square is equal to t. Similarly, the Laplace of t cube is equal to factorial 2 upon s cube. So from here, the Laplace inverse of 1 upon s cube is equal to t cube upon factorial 2, that is t cube upon 2. So this is not your t cube, this is your t square. So this will be your t cube, t square divided by 2. In the second formula, suppose that ft is equal to e to the power minus at or e to the power 80. Suppose that e to the power 80, then the Laplace of ft equal to e to the power 80 dt. We can combine these powers. So this is equal to 0 to infinity e to the power minus s minus a t dt. So on integration, this will give you 1 upon s minus a e to the power s minus a t, and then limits from 0 to infinity. Now here we will assume that s is greater than a, otherwise this power will become minus, and on putting t equal to infinity, this will become e to the power infinity, which is infinity. That means the value is not finite. So we have assumed that s is greater than a. So this is equal to, now on putting the upper limit, this will become now minus e to the power minus infinity, which is 0, and the lower limit will be e to the power minus 0, that is minus 1. So it is equal to 1 upon s minus a. Therefore, Laplace e to the power 80 is equal to 1 upon s minus a whenever your s is greater than a. Similarly, the Laplace of e to the power minus 80 is equal to 1 upon s plus a, and your s is, and there is no need to write any condition on s. So this was the Laplace transformation of e to the power 80. Then the Laplace of sin 80. Laplace of sin 80, where a is some constant, is equal to your a upon s square plus a square. Similarly, the Laplace of cos 80 is equal to s upon s square plus a square. So proof. So Laplace sine 80, now use your definition, 0 to infinity e to the power minus st into sine 80 dt equal to e to the power minus st upon s square plus a square. Then the coefficient of t is minus s sine 80. Then we have the minus sign, and then the derivative of this sine 80, which is your a times cos 80, and then the limits from 0 to infinity. So on putting our limit, we will get the upper limit as 0 because we will have e to the power minus infinity. So upper limit is 0. So on putting the lower limit, that is t equal to 0, we will have sine 0, that is 0, and cos 0 is 1. So we will have minus a, and one negative sign will come from the lower limit. So this is equal to a upon s square plus a square. Similarly, the Laplace of cos 80 is equal to 0 to infinity e to the power minus st cos 80 dt. And again, using the definition of the property of the definite integral, this is equal to minus s cos 80, then the differentiation of cos 80, which is equal to minus, so it is plus a times sine 80, and the limits are from 0 to infinity. Again, our upper limit will be e to the power minus infinity, which is 0, and our lower limit will become plus s, because cos 0 will be 1 and sine 0 is 0. So this is equal to s upon s square plus a square. Then we have a formula for the Laplace of sine hyperbolic 80 and cos hyperbolic 80. Before that, I will discuss the linear property of Laplace transform. If ft and gt are two functions of t where my t is greater than or equal to 0, then the Laplace of ft plus gt is equal to Laplace of ft plus Laplace of gt. Similarly, if there is negative sign, we will have a negative sign at this place. So Laplace of ft plus minus gt is equal to Laplace of ft plus minus Laplace of gt. Now coming to the Laplace of sine hyperbolic 80. Okay, we know that the definition of sine hyperbolic 80 is 1 by 2 e to the power 80 minus e to the power minus 80 divided by 2. So using this linear property, this will be your Laplace of e to the power 80 minus Laplace of e to the power minus 80. And this is equal to, now we have the formula for Laplace e to the power 80, which is your 1 upon s minus a, and this will be 1 upon s plus a, where my s has to be greater than a because of this condition. So this is equal to 1 by 2. Here we will have s plus a and here minus s plus a, that means 2a upon s square minus a square. So this is a upon s square minus a square, but remember s is greater than a. Thus we can say that Laplace of sine 80, so sine hyperbolic 80 is equal to a upon s square minus a square, where s is greater than a. Similarly, for cos hyperbolic 80, Laplace cos hyperbolic 80 is equal to half Laplace of e to the power 80 plus Laplace of e to the power minus 80, because for cos hyperbolic 80 we have the positive sign at this place. So we will get this equation, and which is equal to 1 upon s minus a plus 1 upon s plus a. So on solving we will get s upon s square minus a square. Again, s has to be greater than a. So these are the some basic formulae for the Laplace transformation. Now we have some important properties. For that I am going to discuss the first shifting property. first shifting property. If Laplace of ft is equal to fs, that means I am assuming that the Laplace of ft is finite. It means the function ft is sectionally continuous and of exponential order. So if the Laplace of ft is some finite function in terms of s, then the Laplace of each power st ft, so each power at ft will be shifted by a. So this is equal to fs minus a, and this can be also written as fs, where my limit s tends to s minus a. So that means if we multiply ft by e to power at, then our s will be shifted by s minus a. That is why we are calling it as a shifting property. So Laplace of each power at ft equal to fs minus a, or you can say the value of fs at s minus a. The proof is very quite easy. So Laplace of ft, Laplace of each power at ft is equal to, use our definition, which is equal to 0 to infinity e to power minus st ft. Ft means e to power at into ft. This is our current function. So we can combine these two power. Taking minus sign common, we will have this thing. If you remember the definition of the Laplace ft, your Laplace ft was 0 to infinity e to power minus st ft dt, and this was denoted by f of s. Now in place of s, we have s minus a. So this will be your fs minus a. That means whenever we have s, we got fs. Now we have s minus a, so our answer will be fs minus a. Now if we replace a by minus a, again Laplace of e to power minus at ft will be equal to fs plus a, and this can be also written as the value of s at s plus a. For example, as we know that the Laplace of sin t is equal to, use the definition of sin at, Laplace sin at is equal to a upon s square plus a square. Now in place of a we have 1, so this is your 1 upon s square plus 1. Now using the definition of this first shifting property, the Laplace of e to power minus t, say this is your fs. The Laplace of e to power minus t is sin t. What will be the value of this one? Just this property. The Laplace of e to power at ft is equal to s minus a. That means our s is replaced by s minus a, where a is the power of, where a is the multiplier of t. Now here the t is multiplied by minus 1, so our answer will be f s minus a, where a is minus 1, so this will be your f s plus 1. That means we will replace our s by s plus 1. So our answer is this one. So Laplace of e to power minus t sin t will be 1 upon s plus 1 whole square plus 1. Just remember that we have to replace s by s minus a. In our case, a is minus 1, so we have replaced our s by s plus 1. Now what is the important part? The important part of this property is to guess the inverse Laplace transform. So the inverse of 1 upon s plus 1 square plus 1 is equal to e to power minus t sin t. And this is very important for the inverse Laplace transformation, because at that place we will solve some partial differential equation, ordinary differential equation. At that time we will need such type of formula. So the Laplace inverse of 1 upon s plus 1 whole square plus 1 is equal to e to power minus t sin t. Again, the Laplace inverse of s plus 1 upon s plus 1 whole square plus 1 will be, now here you can see that s is replaced by s plus 1. So that means there will be some e power minus t because our s is replaced by s plus 1. So we will get some e power minus t, and then it will be your s upon s square plus 1, and this was your cos t. So the Laplace inverse of 1 upon s plus 1 upon s plus 1 whole square plus 1 is equal to e power minus t cos t. Then I am moving towards the unit step function, which is also known as Heaviside unit step function. Heaviside was the electrical engineer, and he gave the definition that the unit step function of t is equal to 0 if t is less than 0, and this is 1 if t is greater than or equal to 0. So you can guess, if t is x-axis and ut is the y-axis, then we are saying that ut is 1, that means this is 1. If our t is greater than or equal to 0, that means if t is greater than or equal to 0, then our t is some, here say ut is 1, and for the t less than 0 the function is negative. The function for t less than 0, the value of the function is 0. And the shifted unit step function is ut minus a is equal to 1, or you can say 0 if t is less than a, and it is 1 if t is less than a, and it is 1 if t is greater than or equal to a. So that means this is 1 if t is greater than some a. So on this side your ut is this unit, which is your 1, and if t is less than a, the value of ut is 0. So the Laplace of ut minus a is equal to e power minus as upon s. The proof: Laplace of ut minus a, you can use the definition of Laplace, that is equal to 0 to infinity e power minus st u t minus a dt. Now whenever your t is greater than a, the value of ut minus a is 1, and whenever your t is less than a, the value of ut minus a is 0. So we can see that there is discontinuity at t equal to a, so we will break it in two parts, from 0 to a, then from a to infinity. So whenever your t is less than a, the value of ut minus a is 0. So the first term will get 0, and in the second term our t is greater than a. Now if t is greater than a, then ut minus a is 1. So this is your e power minus st dt. So on integrating we will get this one, and the upper limit will get 0 because e to the power minus infinity is 0. So we have e power minus as upon s. Thus the Laplace of ut minus a is equal to e to the power minus as upon s. Then we have the third property, that is known as change of scale property. Suppose that if Laplace of ft is equal to fs, then again, provided that the function is sectionally continuous and is of exponential order, then the Laplace of fat, that means we have taken some multiplier a, is equal to 1 upon a fs upon a. That means we will have a number 1 by a at this place, and our s will be replaced by s upon a. So the Laplace of f(at) will be equal to 0 to infinity e to the power minus st f of at dt. So let us assume at equal to u, because we need f of s. For f of s we will have ft at this place. So let us assume that at equal to u. So on differentiating it, we will get dt equal to du upon a, and limits will be from, if your t is 0, then u is 0, and if t is infinity, u is infinity. Therefore, Laplace of f(at) is equal to 0 to infinity e to the power minus s. In place of t, we have u upon a, f of u, and du upon a. So this is equal to 1 upon a, 0 to infinity e to the power minus s upon a, u, f, u, du. So in the definition of Laplace transformation, we have 0 to infinity e to the power minus st ft dt. So in place of s, now we are getting s upon a. So this is your f s upon a. This was the definition of Laplace ft, which is your fs. Now in place of s, we have s upon a. So this will be your 1 by a f s upon a. So now we have the second shifting property. Suppose that if Laplace of ft is equal to fs, that means the function is sectionally continuous and of exponential order alpha when your s is greater than alpha, then the Laplace of ft minus a ut minus a is equal to e to the power minus as into fs. So the Laplace of ft minus a ut minus a is equal to e to the power minus as fs, where ft minus a into ut minus a will be equal to 1, because ut minus a is 1 when your t is greater than a, or 0 or when t is greater than a or equal to a, and it was 0 when t less than a. So this will be your, now this is your 1, so it will be your ft minus a. So as ut minus a was 1, so this will be your ft minus a when t is greater than or equal to a, and it is 0 when t is less than a. So proof: the Laplace of ft minus a ut minus a, use the definition, this will be a 0 to infinity e to the power minus st ft minus a ut minus a dt. Okay. Again, you can see that we have discontinuity at t equal to a, so we will break this integral in two parts, from 0 to a e to the power minus st ft minus a ut minus a dt, then from a to infinity e to the power minus st ft minus a ut minus a. So you can see that at when your limits are less than, when your t is less than a, that means in this part here your t is less than a, the value of ft minus ut minus a is 0. So this term will get vanished, and in this part the value of ft minus a ut minus a is ft minus a. So the first part is 0, and in the second part we have a to infinity e to the power minus st, and now the value of ft minus a ut minus a is ft minus a, because your t is greater than a. So this is 0, this is your ft minus a dt. So now just assume t minus a is equal to s. So let t minus a equal to s, then now your limit will be, if your t is a, then s, if your t is a, then your, say this is your u, because we have already assumed s. So now if your t is a, then your u will be 0. Now if t is infinity, then u will be infinity, and on differentiation we will get dt equal to du. So Laplace of ft minus a ut minus a is equal to, if t equal to a, then u was 0, so the limits are from 0 to infinity, e to the power minus s. In place of t we will have u plus a, and ft minus a will be your f of u into du. So if you take common e to the power minus as, then this will be your e to the power minus su fu du. And this was the definition of Laplace of ft, 0 to infinity e to the power minus st ft dt. So this is your e to the power minus as into f of s. Okay, that's all for today. Thank you so much for being a part of this lecture.